So, in the last classes we were talking about finding rather how to compute things, how to talking about normal and abnormal multipliers. So, just to recall that the Fridtjof multiplier set can be written like this. This is associated with f and this is associated with g and this is associated with h. This is greater than equal to 0, this is in Rm plus and this is in Rk plus Rk whatever be the number of equality constraints. So, and we were calling this to be normal if lambda naught is strictly bigger than 0, we were calling this to be abnormal. Now, how can I guarantee that all my multipliers would be normal? That is a very, very fundamental question. So, let me ask this question: how can I guarantee that all my multipliers would be normal? All my multipliers would be normal. That is the worst thing. We are all surrounded by waves which are not good for us anyway. So, how can I guarantee that all my multipliers would be normal? Now, in order to guarantee that, I would look into the equation, look into the Fridtjof condition, to the John conditions. So, it would be good if I shift to the blackboard to explain you this fact. So, what happens is that this is my John condition, the first line of the John condition. So, if x star is my solution, local minimum, so my John condition says that this expression is equal to 0. Grad g I x star plus summation I is equal to, or j is equal to 1 to k mu j grad h j x star. And of course, you know the other fundamental conditions that lambda I g I x star would be equal to 0. This is 1 and this is 2. And of course, the most important of all the conditions is as we have written in this slide. This is what is said. Now, I know that if I is not in the active index set, that is, if I define this particular set called the active index set, which we have already mentioned before. So, I is some number, some index between 1 to m, and take all those indexes for which g I x bar is equal to 0. So, if I is not element of I x naught, then this condition number 2 would imply that lambda I is equal to 0, because a product has to be 0. If one of them is not, one of them is strictly less than 0, the other has to be 0. So, that is the meaning of complementary slackness, that both of them cannot hold with strict inequalities at the same time. So, I can then rewrite this upper part in a slightly simple way. That here I replace this whole summation with the fact that I belongs to I x bar j is equal to 1 to k mu j Now, let us examine the situation what would happen if lambda naught is equal to 0. So, if lambda naught is equal to 0, it would imply that 0 must be equal to and lambda I, which means the set of all the vectors, all the this is a vector consisting of all the components of lambda corresponding to I element of I x bar. So, lambda I is equal to lambda I, these vectors where I belongs to I x bar. So, this vector now, because lambda naught is 0, but the whole vector cannot be 0, whole set of multipliers. So, this two part now has to be non-zero, lambda I and mu, this part has to be not equal to 0, right. So, it means that if lambda naught is equal to 0, then this would be 0 with this not equal to 0, this vector not equal to 0. So, lambda not equal to 0 implies these two conditions. So, if this condition fails, then lambda naught is not equal to 0, can never be equal to 0, which means what is the meaning of failure of this condition, which means if we have 0 element of summation I element of I x bar lambda I So, if we have this with lambda I greater than equal to 0, then it implies that this lambda I vector is 0 and then mu vector is 0. So, whenever I can have a condition like this, then this lambda I and mu j, all of these, all the lambda i's with I belonging to I x bar and mu j with j in j from 1 to k, that should be 0. So, this condition is sometimes referred to as the basic constant qualification. So, it is a qualifying condition on the constraint which is always guaranteeing me that lambda naught cannot be equal to 0. So, you can make up your own theorem which would say, so we say that this means that the basic constant qualification at the point reference point x star at the local minima, if x star is a local minimum and BCQ, basic constant qualification, or BCQ holds at x star, if this happens, then if this holds at x star, then all the John multipliers are normal. So, if BCQ fails, means if this happens, that is lambda and mu is not equal to 0, but still we get this equal to 0, this sum of these vectors, then it means that there would exist at least one abnormal multiplier. If BCQ fails, then there exists at least one at least one abnormal multiplier. Then there exists, which is a sign used by mathematicians, at least one abnormal multiplier. Now the interesting question is, if I have a situation where my BCQ has failed and I know that there exists an abnormal multiplier, can I still say or show by an example that okay, even if I have a abnormal multiplier, but I can find another multiplier vector, set of multiplier vector, another set of lambda naught lambda mu, for which lambda naught would be strictly greater than 0 and corresponding to the same point x star. So if BCQ fails, we say x star is a irregular point. Now is a part of ongoing research as to how to address the situation when my BCQ has failed. When my BCQ has failed, how do I address the situation? How can I guarantee that in spite or under what conditions can I guarantee that in spite of the failure of the basic constant qualification, there would exist at least one multiplier which would be a normal multiplier, and that is a piece of interesting research, because all the so called constant qualifications which are weaker than BCQ, there are like Abedi, Gignard, which we will not discuss in this course. So all of them which are weaker than BCQ can only guarantee that there would exist one normal multiplier, but they cannot guarantee that all the multipliers are normal. The strong, or rather the weakest possible constant qualification which will guarantee that all the multipliers are normal is the basic constant qualification. The basic constant qualification also has an alternative form obtained in 1967 by Mangasarian and Fromovich. That is why this is also known as the Mangasarian-Fromovich constant qualification, alternative equivalent form of BCQ. So what is the meaning of this, how to get this alternative equivalent form? So let me write down the alternative equivalent form first, and then we will see how to obtain that. We say that MFCQ, CQ means constant qualification, I will write what is MF, that is called Mangasarian-Fromovich. So we say that MFCQ, this is in short MFCQ, MFCQ holds at x star. Of course, x star is the local minimum or feasible point, I am not repeating that fact. If set of vectors is linearly independent, k x star. and there exists D element of Rn such that actually these are nothing but applications of the separation theorems, but we have not done separation theorem in that great detail that we have done in the convex optimization course. So, we would just show the theorem of the alternative that is used to come from BCQ to MFCQ. So, Ix bar is the same as the Ix bar given on the board, and sorry, not X bar, it is X star. Now, how have I come to this? That is a very, very important thing. For this, we actually apply what is called the Mokins theorem of alternative. Okay. Now, let us first mention, we will mention the Mokins theorem alternative from this book, the Foundations of Optimization by Osman Guler, and I have already mentioned this book at the beginning. Please note, take care that this book is very, very useful for anybody who likes to do some advanced study in optimization, excellent book. So, now we will mention that and we will apply the Mokins alternative theorem to come to our conclusion, but please note one very important fact. The fact is the following, that this fact stands independent of what we are going to do, because this has to be linearly independent. Suppose these gradients are not linearly independent, they are linearly dependent, then there must be some mu j non-zero for which this is equal to 0. So, then I can take all the lambda i's to be 0 and add it with this to get that is totally equal to 0. So, it means that whenever this is linearly dependent, that is whenever k is bigger than or equal bigger than n, strictly bigger than n, then the the BCQ will always fail. So, this number of constraints are also very, very important at this juncture, that if k is strictly bigger than n, it would imply the failure of BCQ. So, if your number of equality constraints is very large and they are not linear, then it is a very, very clear fact that the BCQ would fail. So, in many application problems the BCQ is actually failing. So, we cannot always say that all our multipliers would be normal. So, this is a very mathematical or theoretical practice to have normal multipliers. So, let us write down the MFCQ once again and then show that it is equivalent to what is been said as the BCQ. So, BCQ and MFCQ are equivalent. So, I can go from the BCQ to MFCQ and MFCQ to BCQ. So, MFCQ at x star. So, which means grad H1 x star, grad H k x star is linearly independent and there exists D element of Rn such that grad of Gi x star D So, this is what we will have. Now, let us assume that the MFCQ is true. MFCQ is true means if this is linearly independent, then which means that all the lambda i's here cannot be 0. So, if this is linearly independent, if this is true, so I am assuming that MFCQ holds at x star, then this would imply that lambda of I, this is not equal to 0. This will automatically imply that. Okay. Now, what would these two conditions imply? That these two conditions from Mokins theorem of the alternative, I am just writing down the Mokins theorem. Mokins theorem of the alternative. Now, in Mokins theorem of the alternative, there are two systems and both of them cannot have solutions at the same time. That is the meaning of the theorem of the alternative. So, in the Mokins theorem of the alternative, suppose I have this system, so sorry, this is I equal to 1 2. I am just writing whatever is written in Goulet, so that it is absolutely clearly written. Now, this is one system. So, there are a combination of strict inequalities, less than equal to type and equality, and the second system is this. Here you would actually take lambda I, that is lambda 1 to lambda m L. This is all greater than equal to 0, but lambda is not equal to 0, and you will have the vector mu j's, mu 1, mu 2, mu m, this is greater than equal to 0, while that delta 1, delta 2, delta p, this is in or p. So, these are the two systems. Either there is an x which solves this, if there is an x which solves this, then this system will not have a solution. So, here in the Mangelsdorff constant qualification, there are these two systems. These two systems does not have a solution, which means that this plus, I just have to bother about, I do not have to bother about this, I have to bother about these two, which means that this is holding with lambda I greater than equal to 0, of course, which if this system has a solution, that is there is a D which satisfies this system. So, this system cannot have a solution, which means that there cannot be any lambda where all the lambda i's are greater than equal to 0, but lambda as a vector is not equal to 0, and mu j is in R k, such that this system has a solution, that is 0, that is for those lambda and mu, there will this whole all the vector would sum up to 0. So, there cannot be any lambda of this sort, that there cannot be any lambda, right. So, which means that if this system has a solution, then this system cannot have a solution, which means there will be at least one non-zero element here, and by the application of the Mokins alternative theorem we know that this lambda has to be always greater than equal to this lambda, all the lambda has to be greater than equal to 0 and the whole vector lambda I cannot be equal to 0. So, that we immediately know. So, which means that this system, this BCQ does not hold. Now, on the reverse, suppose you have a system where you know that the BCQ is holding, which means, so what does it mean? That if this system has a solution, then this system means this is, sorry I am making a mistake, I will just come back once again. What I am showing is that if this system has a solution just by looking at this, which means the first system of Mokins alternative theorem has a solution, so the second system will not have a solution. So, if this system has a solution, so this system cannot have a solution, and in this system we will have lambda I not equal to 0 given by the Mokins alternative theorem. So, this once I know that this is not equal to 0 and this is equal to 0, I know that this system, there is this, so there is lambda I vector not equal to 0. So, there cannot be any lambda I vector equal to 0, not equal to 0, and any mu in Rk for which this will be equal to true, which means if this system has a solution, this system cannot have a solution, which means this is what will happen, which means this the BCQ will hold. Now, suppose the BCQ is holding, this system is holding, that is this system has failed. Now, because this is, we have assumed separately that this is linearly independent. Now, if this is linearly independent, I am guaranteed that lambda has to be greater than equal to 0, because if not, I said that this is holding, that is there cannot be any non-zero lambdas and mu's which will make this vector equal to 0. So, if I now say that no, the lambdas can be all 0, if all the lambdas are 0, then some of the mu's has to be non-zero if this system does not have a solution, right, which means grad Hj bar would be linearly dependent. Once again, this is a very crucial fact. So, I know that there is no solution for this system. Now, because of the fact that grad Hj bar are all linearly independent, if this system because of this system is not having a solution and all the grad Hj bar linearly independent, I must have tau to be greater than equal to 0, because if tau is not all equal to 0 and this is linearly dependent, then I can put mu j, equal to some mu j would be non-zero, and then I put all the lambda is 0 and make this 0, which will be contradictory to the fact that this system cannot have a solution, non-zero solution, but that there cannot be lambdas and mu j's all non-zero and which add up to 0, which means that the linear independence of the gradients is imposing the fact that this system does not have a solution, with the additional fact that lambda I, this vector cannot be equal to 0. Then now by going, I know now that this type of system does not have a solution, so this system has a solution, which means now going back there would be a D for which this system would have a solution. So, what we have shown is that if this is assumed, okay, this is a part of MFCQ, that MFCQ in fact, so if MFCQ holds, all these holds, this will be true, this has to be true, this cannot have a solution, right. And if BCQ holds, it is immediate that this grad HS would be linearly independent, because if they are not linearly independent, I told you what can happen, then I can show that the BCQ has failed. So, BCQ has hold, this is linearly independent, and if this is linearly independent, then if this is linearly independent, then we have applied Mokins alternative theorem on this part to conclude this thing, and of course, lambda I cannot be all equal to 0. So, here suppose this has a solution, means if lambda is equal to 0. So, what we have done is the following, is that if MFCQ is holding, that is if there is a D such that, then this system cannot have a solution with, of course, the vector lambda I would be not equal to 0, right. And MFCQ holding is, we have already assumed that this is linearly independent, because if this is linearly dependent, then this system anyway has a solution. So, linear independence first has to be given, because if linear dependence is there on this, then BCQ anyway will always fail. So, this plus this shows that BCQ will hold if Mangasarian holds, Mangasarian MFCQ holds. Now, suppose BCQ holds, and that is there is no such lambda i's. If there are no such lambda i's for where this non-zero lambda i's for which this will be equal to 0. So, whenever this happens, these are all equal to 0. So, there exists no lambda I, there is no lambda vector with lambda greater than equal to 0, when lambda greater than equal to 0 and lambda not equal to 0, there is no such vector for which this is holding. So, which is basically this line, no such vector lambda I which is not equal to 0 and greater than 0, and mu not equal to 0 for, or any mu whatever with. So, there is no such vector lambda I greater than equal to 0 and lambda I not equal to 0 or mu not equal to 0, because you see if there exists a vector mu not equal to 0 for which this is holding, and if all the lambda i's are equal to 0, then the BCQ will fail. So, there cannot be any lambda I here not equal to 0 and lambda I greater than equal to 0, that is lambda I all of them are greater than equal to 0 and one of them is strictly 0 for which this is holding, for which this equation would hold. So, BCQ actually, the failure of BCQ is actually some sort of a statement like this, because if I take because what would happen is that once this statement is true, that this system cannot have a solution with this and this not equal to 0 and this not equal to 0, because if this system, if this system has a solution and if this is equal to 0, then it will mean that this is linearly dependent, and linear dependence means the failure of BCQ. So, which means that if you say that BCQ holds, then you must have linear independence of this, right, and when you have linear independence of this, it will always imply that this will be not equal to 0. So, this is a very crucial point to understand. So, this is what is called the failure of the BCQ. Now, if the BCQ fails, but now if you say that BCQ is holding, then this has to be always linearly independent. Now, once you say that it is linearly independent, which means this system cannot have a solution, because if this system has a solution with lambda I greater than equal to 0 and lambda I not equal to 0, which means that this system has failed. So, this system cannot have a solution. Failure of this system, the satisfaction of this system, that whenever I have this would be equal to 0, is a failure of this system, is a failure of this system that I just write down. So, the satisfaction of this system, that if BCQ holds, then this system fails, then this system fails, component wise greater than 0, this system actually fails. So, if this holds, then this system is obviously failing, which means that again if this system holds and whenever I have this is equal to 0, then this system is failing, means that system is failing, which would imply something like this system has a solution and this system has a solution. And obviously, if this system has a solution, this is the system which is true, then this is anyway linearly independent, which is that. So, finally, we have MFCQ is equal to BCQ, and that will end the talk here today, and the next class we will prove that for every linear programming problem, which is for us a very important class of problems, the multipliers would always be normal, it can never be abnormal. And then we will go on to the study of quasi-Newton method using the knowledge of constant optimization that we have got today, but it is very important to note the relation between BCQ and MFCQ through the Mokins alternative theorem. That is why I repeated it constantly to know the difference, and this is a very important difference. Not to know the difference, I would say that to know how to do the equality. So, how to apply the alternative theorem. So, it is very important to note this fact of a satisfaction of this is a failure of this, and hence a failure of this system, hence something would be of this type would be true, and hence this would be true. So, it is not so trivial as you think over it at your home, and we can again discuss if that is necessary.